Philip è anche lui tedesco e parlerà in inglese. Secondo me sarà comunque molto interessante vedere la sua presentazione. Lui si presenta come un computational designer, quindi anche lui applicazioni di computational, ed è anche socio in un'azienda con la sede operativa in Trentino Alto Adige, dove fanno una cosa molto particolare, molto interessante sulla stampa 3D grande formato.
So thanks for staying so long. Thanks for having me, Ricardo. I talk to you about two very specific projects, very down-to-earth projects that both use Rhino and various plugins, some more known, some less known, to actually realize something that is either optimized or automates the workflow. So the first thing is we are based near Bolzano. We're doing 3D concrete printing, but not as you might know it. We're doing it in a particle bed. It's called SPI, for Selective Paste Intrusion. And I'll keep the fabrication part to a minimum. But basically, this method allows us to print in a large-scale particle bed at a high resolution of 3 millimeters. So high-strength concrete also. We're basically free in whatever we want to print. So we've printed structural parts, we've been decorative panels, facade panels, and when I say everything, we actually do print everything. If we run out of friends, we just print ourselves some own friends. And here's a little video of the technology, just so you see what it actually is. This is the particle bed filled with aggregate. Then our main invention is the print head that injects liquid cement paste. And this we've been automating over the past couple of years. Here you can see the bound area, so it's basically like SLS metal printing, just with concrete. And as I said, we can print 15 cubic meters, so fairly large parts, and it's meant to go into building and construction, but it's the initial stages. It's taking a while. 15 cubic meters,
quindi 15 metri cubi.
Esatto.
Così, per dare giusto un numero, ok? Le dimensioni non contano, ma 15 metri cubi sono un bel po' di cemento.
So, the first project I'll be talking about is Bridge the Gap. This has been realized together with the Technical University of Munich and Scawo3D, which is us, as a research project. It was the first project where this technology was actually applied in a structural sense. So the pieces that the bridge is composed of are completely structural. Structure is the main key point. We also have collapsing bridges in Germany, so you don't feel that bad. And this is what we didn't want with that bridge. So we've developed a workflow which centers basically around the material and the structural design, and then goes to manufacturing and assembly. The material is concrete, as I said, high-strength concrete. You can use many different aggregates for it. So we've printed with recycled concrete, lightweight aggregates, and also some other more dense stones. And now this is the workflow. It's not very graphic, but we go through global geometry, segmentation, detailing, and structural analysis. Here you can see a little more what that actually means. And now I'll go quickly into the different steps of this project. So first we start, and it's all based on Rhino. This is why I'm here, I guess.
Not only, but one of the reasons, sure.
Do you want to translate something? No, okay.
No, se era una traduzione direi che ci siamo. No.
Okay. So first step, we have a mesh topology basically, which is the whole input for this project. And we use combinatorial equilibrium modeling, which is a tool developed at ETH Zurich for finding a compression dominant form, which is then so this is kind of the background. We have our mesh topology. We classify the different nodes, and I won't go into detail too much, but we're using graphic statics to actually find that compression dominant form. So here you can see the form diagram and the force diagram, where we use vector-based graphic static, another plugin also running on top of Rhino and Grasshopper. And then we go into subdividing this form-found geometry just by a simple Catmull-Clark subdivision into a thickness and stiffness optimization by a custom vertex morphing application that was developed at Technical University of Munich by a colleague of mine. So this is out of my reach, to be very honest. And here's a video of the process. So starting with the global topology.
Possiamo dire appunto, questo il primo pezzo è la form finding, quindi la ricerca della forma, perché il cemento lavora meglio a compressione, quindi l'obiettivo è cercare una struttura che lavori unicamente o il più possibile a compressione, quindi attraverso una serie di plugin o di tool sviluppati viene fatto questo processo, a partire da una mesh semplificata via via poi si va a rifinire.
Thanks. Moving on, so we somehow need to make these parts manageable in terms of lifting them, assembling them after they have been printed. We use Caramba 3D, also running on Grasshopper, to analyze the principal stress lines, and from this we choose a pattern that allows us to create a bridge that is not forming any hinges. So when you load it, no part will actually geometrically fall out of place. And this we use then to remesh the whole bridge, create the segments, create a joint geometry, so that in the end we have an interlocking pattern of single pieces that don't weigh any more than 140 kilograms, so a forklift can lift them.
How much is the span here?
Sorry, I didn't say. It's 5 meters by 2.5 meters.
Okay.
So it's a smaller bridge.
Smaller, sì, still.
Yes.
5 metri per 2,5, ok,
Yeah.
quindi comunque piccolino per essere un ponte, ma comunque una struttura abbastanza impegnativa. I think it's pedestrian, right?
Yes, well, it was a prototype for a pedestrian bridge, but it would have been pedestrian, yes.
Idealmente per far passare delle persone, però insomma 2 persone, 100 qualcosa chili ci sono, quindi impegnativo. Questo appunto è il video dove mostra come la forma di base viene segmentata, e poi ovviamente c'è il problema di tenere insieme questi segmenti, sempre facendoli lavorare a compressione, in modo che nessuno si faccia male, come si dice.
Yes, and then we have some details in there that are more structural, not so much about Rhino and its application, but we use post-tensioning cables that have printed-in channels.
Is it this a cheating?
Sorry?
The tension cable, is it kind of a cheating?
Well, yes, you're right.
Kidding.
But it would have been the historical context where the bridge would have been constructed that doesn't allow any horizontal support reaction. So we needed them. And it's a nice showcase of what is possible, actually. That's how we justify
it was joking, just a joke. No. Okay. No, dicevo appunto, tutta questa cosa, poi aggiungono i cavi di pretenzionamento che in realtà è una sicurezza in più e serve per evitare movimenti, per esempio di torsione, eccetera. La macchina, avete visto velocissimamente la macchina che hanno costruito, che è una stampante a getto di inchiostro, però l'inchiostro in questo caso è sabbia o comunque materiale cementizio.
Yeah, so I'm just quickly skipping through the videos while you translate, Riccardo. And then we've erected it in Munich, and now I'm quickly jumping to the next project, which is more towards automation. So we've called it 3D Stair Designer. It's a project that we're doing in collaboration with Timo Harbo from Denmark and my company Scawo3D. And it's about automating the staircase design for our 3D printer. So it's not just any staircase, but really we want to take a plan from the customer and transform it into a stair. So if a customer approaches us, basically he asks us, can we print this stair design, which is sometimes a bit difficult. So we then have to get it to a final staircase. In between is our manufacturing. And until we found Timo Harbo, it was a bit like this, the computational design part. There was a lot of meshing, remeshing, going from curves to surfaces, back and forth. It didn't really work out, and then we got Timo on board to actually produce something using some more tools than I could personally use to come up with a workflow that actually automates this all. And here I'm using some of Timo's slides because we want a minimal input for this whole workflow, and this is basically the curve along which you move up a staircase. And you use also the boundaries. So say you have a house and the staircase is enclosed by walls. These are the constraining boundaries of the staircase. Then you also have a height profile. And these are mainly the inputs, or these should be the only inputs we use for generating a staircase. There should not be any more manual interaction with Rhino afterwards. In the end, we want something like this that can be printed. And then eventually came the question of what geometry representation we should actually use to come up with the staircase. So first, we build we start with curves, then we go to surfaces, and eventually we have to come out at a piece that has the resolution of the printer, but not any more than that. So we start with the surfaces that define the underside of the staircases, then we go into meshes, but eventually we found out that meshes are nice, but we need the smoothness of sub-Ds, so we build a sub-D volume along these stringers and underside of the staircase, and there we have the smoothness. And then we have this, but we still need all of the rest that comes on top, so the details inside also, which are used to attach the wood here that is useful for casting in the concrete, and then we have other pieces. For example, we have cutouts here so that the concrete can flow through, and we have attachments for the steel reinforcement that goes in.
Yeah, because you're not making the full stair.
No, exactly. I'll show a video afterwards where they can see it there. Yeah, so a lot of things that need to go in there, and what happens if we want to merge all of this together? Of course, we will be talking about Boolean operations, which become quite challenging at this many pieces that need to be joined. And here, for the central stringer, actually we're using the tool by Daniel Piker, who is also who just presented. So thanks a lot for that, to implicitly define the stringer in the middle, because we have the steps that should be very clearly defined. We have the underside, but all in between is that we know there should be a hole in the stringer, and that's where isopod comes in to implicitly define these areas where there can be a hole. Exactly, and then these are cut out afterwards, where the Boolean comes in, and we use volumetric modeling to actually make that work. So we work with different resolutions. First, we represent the whole staircase in a rough resolution to see if everything is about working, and then we set this constraint of the resolution of the model being just a little smaller than the resolution of the printer, because we don't need it to be too high. We will never be able to realize it. It just needs to be right underneath the printer resolution. Exactly, and this is then the final step, the segmentation and the meshing on the volumetric model.
How much time took to
Yeah, that is a bit of a problem.
this.
So we do it in segments. We don't do the whole staircase in one, but we calculate one segment after another, because it does take a little time, but it works,
Yeah,
at least. With Booleans, we ran into many dead ends.
Yeah, it will cost you much more
Exactly.
time,
So here you can see it. We calculate it section by section, and then we extract the pieces at the end. But the good thing is that it's the whole workflow is non-destructive, so we can go back in the initial stages that are very fastly calculating, and then make changes. And then only once we know it's working, we go into the final export.
Quindi, just a second.
Yes.
Appunto avete visto il processo, è abbastanza articolato, però in realtà ogni passaggio ha un obiettivo molto, molto specifico. Quello che secondo me è interessante è appunto la parte finale, dove ho una serie di geometrie che mi servono costruttivamente e in qualche modo devo, per la stampa 3D, andarle a rendere un unico volume, e la soluzione che hanno trovato è stata quella di generare con isopod le zone di foratura attraverso il campo che si genera fra superficie inferiore e superficie superiore, quindi lì si può facilmente generare una geometria che che è definita, che poi deve essere utilizzata per le booleane. A quel punto l'altro passaggio interessante è l'utilizzo di Dendro, se vi ricordate è uno dei plugin che vi ho suggerito, che fa appunto questa ricostruzione a partire dai voxel, quindi l'intera struttura può essere ricostruita con una serie di voxel, più i voxel sono piccolini più la struttura sarà precisa. Di nuovo il vantaggio qual è? È che si può fare un primo passaggio con una risoluzione piuttosto, avete visto, scadente, molto approssimata, fare le macro verifiche sulla struttura e man mano che il progetto procede anche fare raffinare la mesh fino ad arrivare poi alla mesh finale. La cosa interessante che ha detto per ultimo è che questo processo può diventare iterativo, cioè io posso facilmente, una volta stabilito il processo, posso facilmente ritornare all'inizio e fare una serie di modifiche per poi arrivare in fondo. E yes, the size.
Thanks. Exactly, and then it goes into printing. I won't go too much into detail, but here you can see how it works again. We can print one flight of stairs in one print, and that usually takes 6 to 8 hours. So it's fairly quick for producing such a freeform staircase. Here you can see it in the printer. The next day after printing, we excavate the parts, send them on site.
How many parts you printed in one day?
That was one flight of stairs, so one story.
Ah, ok, quindi
So
una rampa di scale in un giorno, 6-8 ore. Quindi, insomma, se pensate a quanto ci mettono in cantiere a fare una scala elicoidale, probabilmente 4 giorni. Quindi. Can I?
Yes, of course.
I am anticipating the...
Should I continue?
No.
So, well, here you can see how it's constructed on site, and basically the advantage is that in the area of the Alps, and I think globally even speaking, there are not always craftsmen available, or there is not the budget from the person owning the house to construct a freeform staircase like this. So we come in at a cheaper price when it comes to freeform staircases. So this is why we developed this whole workflow, integrating curves, NURBS, implicit and volumetric modeling, because it really allows us to be this free. It's of no use to construct a straight staircase using 3D printing, but it has to be something complex to make it actually viable.
Esatto, come tutte le stampe 3D ha senso se la struttura diventa complessa. Secondo me è interessante notare che non hanno stampato la scala, ma hanno stampato, diciamo, la cassaforma su cui poi costruire la scala, che è una cassaforma, diciamo, a perdere, quindi fa parte integrante del progetto della scala, ma evita appunto di avere manovalanza specializzata, che sappiamo oggi essere un po' un problema, e viene definito digitalmente, quindi con un processo estremamente preciso poi di costruzione. Il risultato it's very, very beautiful.
Thank you so much. Well, they've hidden the concrete, which we don't love that much, but it's still the client staircase. But you can plaster over it, as you can see. This is another stair we've done in Bressanone, and these have been the 2 staircases we have done so far. And well, we're ready to construct more staircases now that we have our own plugin. Yes.
You are releasing it as a plugin?
The
internal
we're
plugin. Internal
undecided.
Plugin.
Yes, for now it's an internal plugin.
Okay.
Maybe one day
No,
after we've constructed some more staircases on our own. Yes, there is a plan, but it's not stable enough yet to be released. It works for us, but not
Thank
for
you,
everybody
Philips.
yet.
Very, very interesting for me.
Thank you.
Thank you.